I'm Daniel Skuka for ESA Web TV. We're in Belgium at European Space Weather Week, and I'm speaking today with Manuela Temmer from the University of Graz in Austria and Richard Horne from the British Antarctic Survey in Cambridge. Thank you very much for joining us. Manuela, my first question is for you. The Sun undergoes some incredible periodic variations and changes. Can you tell us a little bit about what happens with our Sun?
Right, so our Sun has seasons, just like we have on the Earth some weather seasons. It's in principle we have an 11-year-long cycle. So this cycle is covering increased activity and decreased activity. So in total it's an 11-year duration on average. This increased activity is usually related to strong flare emissions. So bright spots, brightness increases at the surface, and coupled to that coronal mass ejections, which are huge explosions from the Sun that can also propagate towards Earth and then interact with the Earth magnetosphere, for example.
Now I understand that during the season of high activity, we're actually seeing more spots on the Sun. Can you tell us a little bit about these spots? What are they actually?
So sunspots are strong magnetic fields on the surface of the Sun. They represent cooler regions compared to the ambient. That's why they appear darker. They can accumulate a lot of energy, magnetic energy, and if there are some disruptions in the magnetic field, they can release that magnetic energy abruptly, and that leads then to flares and also coronal mass ejections.
And that's what we see happening when we see these incredible images of the Sun. We saw this activity on what we see as the surface. It's flaring, and it's these coronal mass ejections coming towards us.
Coronal mass ejections are huge plasma clouds and magnetic fields that are able to propagate towards Earth. So space weather is the radiation and also the plasma clouds when they reach Earth and when they cause a lot of effects. So those effects can be aurorae, so to say a nice space weather effect, but we also have increased radiation doses, especially important for aviation people. We see variations in the Earth magnetic field, so this is usually measured by a so-called KP index. So we see really the magnetic field. If you would go out with a compass, you would see the needle of the compass varying over a certain time range, and this can cause pipeline erosion. We also have increased currents in power lines, and this can eventually also lead to failures of power.
How does space weather affect these satellites in orbit?
Okay, well, I mean, space weather starts with the Sun, but all the impacts are felt around the Earth, and satellites are really one important factor in that. So there's something like 1,600 satellites on orbit right now, and maybe just about half of those are actually at geostationary orbit. So they go around the Earth about once a day, at the same rate that the Earth rotates. So they maintain their position above the same point above the Earth. So they're used mostly for sort of communications, TV, mobile phones. It's an amazing thing which we use these days. Mobile phones is like everybody's got a mobile phone, it seems. So it's really, really important for us. Our modern day life depends on it. So satellites can be damaged by a number of different ways, but one of the most important ways is by high energy charged particles. So the satellites orbit inside the Earth's geomagnetic field, and that extends out to something like 10 Earth radii out on the day side of the Earth. And that acts as a protection for the spacecraft most of the time. But when we have one of these coronal mass ejections, what it does is it drags with it the magnetic field from the Sun, and that then distorts the Earth's magnetic field, disrupts it, it tears apart the outer layers of the Earth's magnetic field, and all hell can break loose when we have a big storm. That's what happened in 2003, that's what happened in 1989, so we've got some really good documented examples. For the average person in the street, how would a loss of satellite services affect them? So I think interruptions to their mobile phones, that's probably the most important thing. Interruptions to GPS signals. I mean, GPS signals are used right the way across the world. It's used in transport, navigation, all kinds of things. It's even used on the stock market to do timing of trading events on the New York and London Stock Exchange. Other examples where you might be affected, loss of TV. If you're broadcasting the Olympic Games and you're doing that across the world and you lose a TV signal, that's bad news. That's bad news, and the World Cup, that kind of thing, especially if England's winning.
Richard, if you could ask a solar physicist any question, what would you like to ask?
What I'd really like to ask is, Can you tell me how long it's going to take for a coronal mass ejection to come from the Sun to the Earth? And how well are you going to be able to predict that? Because we really need those predictions to protect satellites.
So the coronal mass ejection on average needs 2 to 3 days. If we have a very fast coronal mass ejection, they are able to manage below 24 hours. And that's really hard to forecast. So it's in principle, if we would like to forecast coronal mass ejections, we also need to forecast flares. And that's a very tricky business, because for this we need to know the evolution of the magnetic field, so the sunspots that we were talking about earlier. And yeah, that's really, so we haven't found any algorithm yet to really forecast it. So.
What are some of the systems we need to be able to help make these early predictions of coronal mass ejections and solar flares?
So to forecast flares and coronal mass ejections, so the major ingredient, the parameter that we need to know is the magnetic field evolution. And up to now we observe the Sun from the Earth, so we have only the visible surface that we can get measurements from. So we cannot look around the limb, so we need to go off the Sun-Earth line. And so that means also to send a satellite to, for example, the L5 Lagrange point. That's a point 60 degrees off the Sun-Earth line. And from that point we would get the evolution of the magnetic field as early as possible. And with that we could try to forecast the flares and semis.
Manuela, if you could ask an expert on how solar weather affects satellites, what would you want to ask?
So, Richard, the question that I would like to ask is what's the lead time that you actually need to know in advance when a coronal mass ejection is coming, and in what kind of detail you would like to know the variations of the magnetic field?
Okay, well, as far ahead as possible, I think, is the answer. Actually, when I talk to satellite operators, they actually say we want to have some kind of knowledge a day in advance. And at the moment, we just can't do that for good scientific reasons. And we just don't have the observations to do that. If we can get closer with an L5 mission, I think it would actually really help us, But so at the moment, I think we can only make reliable predictions, something like 45 minutes, 1 hour out. We can stretch that to something like 3 hours, but beyond then our predictions become very uncertain, let's put it out, because everything can change so quickly.
Richard Horne and Manuela Temmer, thank you very much for joining us. I'm Daniel Skuka for ESA Web TV. For more information on ESA's activities related to space weather, follow our website at www.esa.int/spaceweather.